Bismillah ar-Rahman ar-Rahim. Today is basically our first official lecture on Verilog. Okay. Uh, of course, I assume that you have been exposed to Verilog before, but consider this lecture to as a mind or as a refresher to your knowledge from before, as well as with some new material in. Okay, there is also a new material that we are covering for the first time. Okay, طيب. And my way of teaching Verilog is through examples. Okay, through examples. I don't like going through slides and the traditional method. I want to write modules right in front of you in order to be able to learn something practical. Okay, so first of all, our toy example for today or for tonight is basically a 2-to-1 multiplexer. Okay, 2-to-1 multiplexer. We all understand how a multiplexer works. Okay, it has basically a selection line. A 2-to-1 multiplexer has a single bit selection line with, of course, it is an n-bit multiplexer. So the width of the input lines are or data lines is n-bit, and the output line is as well n-bit. So the output is going to be input number 0 if S is 0, and input number 1 if S is 1. That's the multiplexer basically, right? So understanding this behavior, we can develop different kinds of modules for a multiplexer. Okay. To start with, we are going to discuss, or I said I misspoke and said modules. I meant to say different kind of models. Okay, different kind of Verilog models. So in Verilog, we have basically 3 models, or more than that, but the main models that we are going to discuss is only 3 models. One of them is called structural model, which is the one that we are going to discuss in a moment. Okay, the other one we will discuss later tonight, inshallah. Hopefully we have time. It's called the Dataflow model, okay, using a sign statement. And the third one is basically behavioral model. So you are describing the behavior rather than the circuit, okay? طيب. So this module here is basically a structural model. What does it mean, the structural model? It means that you are describing the structure of the circuit. How is it composed, gate by gate, okay? So basically structural modeling is equivalent to providing a netlist of the circuit, okay, of the circuit. So basically what we have here, the first line is basically a directive, which probably you haven't seen. You may have seen this in 202, but it is basically a directive, and it is telling the simulator to adjust the time scale. It starts with this symbol here, which is not a single code actually. It is the one. This is the character basically to the left of number 1 in the keyboard. It's not the single code, but it is the character next to the left of left of the number 1 in the keyboard. Okay. Then you say time scale, or by the way, all Verilog directives start with this character. So time scale, this is a directive that defines the time scale of the operations. The unit is 1 nanosecond, and the resolution is 100 picosecond. So if you say, for example, 1.1, a delay of 1.1, we mean here what? 1 nanosecond and 100 picosecond. Okay, this is what it means, and it will become clear when we discuss the delays of these gates here. So this is the directive here. Basically the reason for having this directive is to define a time scale. Okay, time scale. for the simulation. All right. And it has nothing to do with synthesis. Has nothing to do with synthesis, and this is only for simulation purposes. All right, synthesis. What do we mean by synthesis, by the way? Anyone remembers what synthesis mean? Anyone remembers what synthesis means? You guys are talking, or my
تصنيف صحيح.
say it again, please.
Like the translation is تصنيع, or you synthesize and make it from synthesis, right?
Yeah, so synthesis is going from an abstract level to the next, a more detailed level. Okay, this is in general. Okay, in Verilog realm, okay, it is what? It is basically going from a Verilog module to circuit. Okay, providing a circuit. This is part of the skills that you need to learn. Okay, during the course. I mean, we will actually go through this, inshallah, in further details later. But you should be able to know once you know how to model. يعني أول حاجة يعني there is what we call modeling. Modeling is you have an idea in your mind and you model it using Verilog, or you have a circuit and you translate it to Verilog. This is called modeling. Then the reverse way, or the reverse operation, is you go from the model to the circuit. Okay, this is called synthesis. So my statement that I said is that this directive here has nothing to do with synthesis. It is only for simulation purposes. Okay. Right. Next is if you want to define any circuit in Verilog, it is hold on a second. It is a must that you embed it inside what we call a module. Okay, module is the basic entity that embeds circuit basically structures. Okay, so here we give the module a name. So the keyword module starts a module definition. Okay, and then space followed by the module name. This is the module name, and then if you have parameters, you say pound and then list the parameters in this format here, parameter and then n, and then you give it a default value. Okay, and then comma, the other parameter, you give it a default value if you want. Of course, the parameter does not have to have a default value. All right, if it does not have a default value, then you have to supply it its value during instantiation. So the first part after the instance name, the module name, is to provide the parameters. Now the parameters here are if you don't have any parameter, then this is optional. Okay, you don't have to supply it, but the ports are most likely required. Okay, for the circuit to be useful, okay, it has to have interface, either input or output. Maybe it has only outputs, maybe it has I don't know, if it has only inputs without outputs, it may not be that useful. Okay, usually it has inputs and outputs. Now I'm using I'm just listing the names of the ports here. Okay, and then declaring them beneath the module definition here. Okay, so we have I0 being what? I0 is being an input port, okay, of width n minus 1 to 0, so it's n bit basically, and this is I0, comma I1. So I1 is exactly the same as I2. It's input and it's of width n minus 1 to 0, or basically n bit. Now the selection input is S, and it is only 1 bit because you are selecting one of two cases, either 0 or 1. Okay, you don't have to have it like n bit, like I0 and I1. Okay, the output needs to be the same width as I0 and I1 because it is going to receive either I0 or I1. Okay, so we mark input as input, and the output as output. Now there is an implicit what we call keyword here that is omitted. It's called wire. Okay, wire. And this is the keyword here, the wire. Okay, we say here input wire, then you give it the width. Okay, also output wire, then you give it the width. Okay, if you don't mention the data type, it is by default a wire. Okay, the other data types are registers. Okay, registers, and we have also other types, but most likely in this course you are going to work either with wire or register. Similarly for S, you have input wire S. So don't get confused if you see something like this, input wire S, like this. Okay, this wire statement here or wire keyword is optional and it is implicit. This is the implied data type of S if no data type is associated. The other data type, as I mentioned, is reg. Okay, but we don't use reg for structural modeling. Okay, for structural modeling we use only wires. All right. And
Excuse me.
then, yeah, go ahead.
Just يعني, for example, if we use input register, then how is it?
Okay, you are asking about registers now.
Yes.
We are going to come to registers later. Okay. So,
Okay.
do you have a question about the wires now?
No, that's fine.
Yeah. So let's postpone this discussion until we come to that. Okay. So basically, because we have a lot to cover here. Okay. We have here internal signals called T0 and T1. All right. And these internal signals are required to calculate. This is basically the logic for the multiplexer. The y as a signal equals what? S complement into I0 ORed with S into I1, right? I mean, ANDed with, huh? And you can say here and to be just very clear, and okay. But S, notice that S is 1 bit and I is n bit. So we need to replicate S by n bit in order for this operation to be correct, because this AND here is basically bitwise AND, okay? Now we need T0 to be this one and T1 to be this one. And then my final Y will be the ORing of T0 and T1, okay? Now for structural model, we use the primitive gates and an OR and not and whatnot, okay? Now these primitive gates only provide what we call single bit operation. They cannot provide bit vector, okay? They cannot deal with bit vector. So I cannot say here, for example, and then I give it T0, and then let's say S complement is what? Let me do T1, okay? So it's S and T1, okay? First of all, I need to replicate S by n times, okay, to AND it with, or bitwise AND it with T1. Okay, if this works, then perfect. But this doesn't work actually. Why? Because AND, the primitive gate AND and OR and NOT, they only take single bit input. This can work if you want to do it this way, T0, and then S only, and then T1, not T1. This is not T1 actually. This is I1, yeah? Okay, I1 0. All right, because you see here S and you do it I1. Okay, and then you do it for the rest of them. But the problem is we don't know n ahead of time, right? So we need to have a loop for this. And the way to do the loop is through generate block. Okay, it's called a generate block. So first of all, you create a generate variable, called I, genvar I. So we create this variable, which is basically nothing but an integer. It becomes an integer because we want to iterate through the creation of the circuit. And then I have my generate and end generate, and end generate. Okay, here, this is end generate. And then I have my for loop here. Okay, and inside the for loop, I have a for I equals 0, I less than n, and I equal I plus 1. And then I have the creation of the two AND gates and one OR gate. Okay, so the first AND gate is for creating T0, bit number I of T0. Okay, that's what? Not S and I0 of I. You see? I0 of I. So I'm just ANDing a single bit here with another single bit to get a single bit. Okay, for every I. And then the other one is for T1, bit number I of T1. Okay, I'm ANDing S with I1, bit number I of I1. Okay. And then to generate bit number I of the output, I just OR T0, bit number I of T0 and bit number I of T1. This is exactly what bitwise operation mean, okay? And I'm adding here a simple 100 picosecond delay for each one of these gates to make the simulation more realistic, okay? And by the way, 100 picosecond is too much for today's technology. I mean, for today's technology, I don't expect it exceeds probably 20 picoseconds or so. So 100 is overestimated, okay? So basically, why is this 100? Because it is a delay of 0.1. So 0.1 means 100 picosecond. The resolution here is 100 picosecond. If you want, for example, to say, well, 130 picosecond, then you say like this, 0.13. All right. So what is the delay of the entire multiplexer? Who can tell me what is the delay of the entire multiplexer? The worst case delay?
200 picoseconds.
200 picosecond. Excellent. Okay. But if I say, for example, I change this to 2. What happens? What is the delay now? The worst case delay. The 300. Excellent. Yeah, 300. All right. So I'm going to leave it like this. Any question about the generate statement? Shabab?
Yes, about the delay. Now, what if we 100? Not 100. If we wrote 1.
If you write just
then,
1, like this, yani.
Yes.
Okay, this is going to be
And
1 nanosecond. 1 nanosecond. This is the time unit. Okay, the resolution is what comes after the decimal place.
Okay.
Okay, this is going to be multiplied. This one here, this 0.1 is going to be multiplied by the 100 here. Okay, it becomes 100 exactly. 0.1 means 100. So every 0.1 becomes the unit that is provided here. Okay. So the entire thing here is going to be 1100 basically, 1100 picosecond. Okay, which is 1 nanosecond plus 100 nanosecond. Okay.
Yes.
So
and what do we mean?
What do we mean by what?
Exactly in resolution.
Yeah, resolution means the time step at which the simulation proceeds. Okay, يعني خلاص the simulator will not change anything within 100 picosecond. Okay, this is the resolution of the simulation. Again, all of this, even this one here, if this delay here has nothing to do with synthesis. Okay, it's only for simulation purposes. Okay, they're trying to make your circuit behaves as much as possible similar to the hardware, because hardware usually has some delay. Yeah, it's not just delay less. Okay. So hardware usually has delay, and we are trying to mimic that delay by inserting gate delays here. All right. Any question about generate again, Shabab?
Doctor,
Yeah.
for line 14, it will finish the first bit of T0, then it go to the first bit of T1, or it will finish all the bits of T0.
No. The entire thing in hardware, all of the gates are going to operate in parallel. All of the gates. Okay.
So it will
hardware,
finish
remember,
T0, T1, and Y1 at the same time. Then it go for the next second bit for all of
yeah,
them.
here we are just this generate, okay, will basically what will it do? Yani this generate is only for the compiler, for the Verilog compiler, okay? To basically it will replace this generate and end generate by another structure, okay, in which it will unroll the loop here. Will unroll the loop. Yani all of these will become, for example, if n is 4, then you'll have 4 times 3 lines, 12 lines basically of these structures here. Okay, 3, 2 AND gate followed by an OR gate, 3 times. Okay, if n is 4. If n is 4, then it is 4 times, repeated 4 times, 1 time per bit. Okay, and then it will add some changes to the instant name. This is the gate name, by the way, and it will add some random text to the to make this instance unique. Okay, so again, all of this is going to be super clear after you simulate and check the what we call the BCD file, value change dump file. Okay, you will see the generated what we call instances. They are not actually just 3, okay, but rather they are going to be n times 3 or 3n. Okay. And all of these gates are going to operate in parallel. In parallel means I'm not talking about the signal propagation between them. No, I'm talking about these gates are going to operate in parallel. Okay, regardless of which signal they are operating on. Okay.
Okay, thank you.
Sure. Okay, so if no questions are there about this basically module, and I think we better look at the test bench. Okay, the test bench for this case. Okay, I'm going to create what we call, for this course, we are going to talk about or create what we call comprehensive test benches. Okay, a test bench that basically tells you whether your circuit matches a golden output or not, a ground truth. Okay, we have a file that contains the ground truth. Okay, so I'm going to create a file, an input file, okay, that contains the input patterns that tests as much as possible from the input space, okay, usually using random data, okay, but high enough number is sufficient. Okay, usually random data with lots of patterns. Okay, it does a good job in testing the entire circuit. Okay, so this test file as well as the golden output can be basically generated by Python scripts basically. Okay, so even in your project, basically, the first milestone is to generate a Python file to basically process the input and produce the output. Okay, so this basically Python file is going to serve as your golden output generator. It does generate the ground truth information. So if, for example, your circuit produces some other value, you know that your circuit is wrong, because you know the ground truth is generated by the golden file generator. And in my case here, for the 2-to-1 multiplexer, I have written a simple Python script here that does generate 100 test patterns for basically 4-bit, okay, 4-bit multiplexer. And I'm just giving it, parameterizing it here for input file name, output file name. So the input file name is called input patterns.txt, and then the output file name is called golden results.txt. Both files are going to be generated in this Python script. Okay, I have a helper function here that generates random bits. Okay, and it is as described here. It's very simple. I'm just generating in bit that are random. So I'm joining basically either a 0 or a 1, 50% chance for each one of them, and n of them. Okay, so this is basically what it means in Python. I'm generating basically either a 0 or a 1 for n times, and then joining the result as a string. Okay, this basically line here or function generates a string of n random bit. I'm going to use this because in my multiplexer I have a 4-bit input, right? 4-bit input that I need to generate randomly. All right. Now this is the main part of the file. We have basically to open the input file for writing, also the output file for writing as well. Okay, so input file as input file and output file as output file. Okay, so
Sorry,
we
Doctor,
have, yeah, go ahead.
but your voice is lagging. I don't know if the problem from me or from you.
Anyone is having the same problem? Are you? Am I
Yes.
cutting off, ya Shabab?
Yes, a little cutting off, yes.
Okay, I hope that the recording will become clearer. But right now, which part was did you miss, by the way?
About here, actually
Line
there are
number,
many parts, but
line number
last
what?
one, in last part in line number 16.
15? 16.
16.
Okay, so basically this is just opening the files for writing. Okay, opening both files for writing. Okay, the input file and the golden file. All right.
And this is
Yeah.
a Python code.
Yeah, this is Python code. Yes, yes. This is a Python code to generate the golden output and the input patterns. Okay, you got it, guys?
And what do we mean in golden outputs?
This is which one is what? The golden output?
Yes, what do we mean in golden outputs?
Okay, oh, all right. So probably because I was cutting off, you didn't hear me when I said it. So I said that the golden output means the ground truth output. Yani when I give you an input pattern, okay, your circuit will generate an output, صح?
Yes.
Yeah? Okay, so when your circuit generates an output, how do I know this output is correct or not? Huh? I have to compare it to a baseline output, صح?
Which is
This
called the
baseline
golden result.
this baseline output is called the golden output, okay, or the ground truth output, and I'm generating this output with this Python script here. Okay,
Okay.
you got it, yeah, Hassan?
Yes, yes, yes.
Okay, so basically the first loop here, or basically it's only loop, I think. Yeah, it's the only loop. So the loop here generates for n test the number of test vectors basically that you want to generate, and then I0 is random bits of n width, of n size, and then I1 is random bits of n as well, and then S is only 1 bit, so it's a random choice of 0 or 1. All right, and then we say we have I0 and I1 and S, so we can actually simulate the behavior of the multiplexer in Python using an if statement, or using just a Python way of doing it. So expected Y is going to be I0 if S is 0, else it is I1. Okay, this is exactly how a multiplexer works, right? Then we say, well, input file write. Okay, we are writing it as a formatted string I0, comma, I1, comma, S. This is the input file. And then the output file will write only the expected output for this pattern. Okay, so basically the input line number 1 corresponds to input to output line number 1 in the two files. Okay, and then we say here generated num tests vectors in input file and expected result in output file. Okay, so let me switch to the. Let me first of all, before you ask, please, can I just run this code and show you the files that are generated? Let me just run it and show you what the. So let me just first of all remove the files. Okay, and then say here Python 3, and then what? Generate test files. Okay. Now we generated 100 tests. Okay, so if we want to test or show the input patterns, can show the input patterns. At least it looks like this. It's nothing but a comma separated values of different input pattern. Each input pattern is in one line. Okay.
We're
We can only see the code. We can only see the code, Doctor. We can't see the output.
You can't hear me?
We can't see the output.
Okay.
Yes.
Right, let me do that again. A new share, and then can you see it now?
Yes.
Yes.
Okay, so let me remove the two files again, and then run the Python file. Okay, so it generated 100 test vectors for okay, it basically generated these two files. Okay, and then you can just less or output the input pattern.txt, and you can see that it is basically a comma separated file. Okay, nothing but a text file. It is comma separated. Where is the output for this pattern here? It is stored in the golden output. Yeah. So if you look at the golden output, this output here corresponds to the inputs in the first line of the input patterns file. And this output here corresponds to the inputs, the second line in the input patterns file, and so on and so forth. Okay. All right, you got it, guys. So this is how we can generate the golden output and the input patterns file. Okay. طيب, now it's time to look at the test bench. We want to write a comprehensive test bench. The test bench, as you can imagine, should do what? Should basically read this input pattern file, and produces the result in Verilog. Okay, and then what will it do? It will compare the result as obtained by Verilog simulation with the golden output. Okay, well, this is exactly what it does. So first of all, again, I have to use the same scale here. Okay, and then I have my tb.max 2 to 1, and then I have just the parameter here, definition of that parameter, n equals 4, and then I'm just using declaring my registers I0 and I1 and S as well, because I want to drive them during the initial block. All right, and then I want to observe Y, and I have another register for expected Y, which I will read from a file. Okay, I have then the file descriptors here for input file and output file, and also I have values for the returned scanf functions, okay, or system functions. I have error count. I forgot what R is. We will see what R is during the code. This is basically instantiating the mux here, right? I'm using n, which is a parameter here in the test bench, and the unit under test as the instance name, and I'm using basically name binding for port binding here. Okay, .I0 is I0, .I1 is I1, .S is S, and .Y is Y. All right. And now, if you use name binding, then the order does not matter. You can list them in any order you like. But if you are using basically order for the what we call the ports, then you must respect the order. Okay. Now for the initial block for the test bench, okay, I'm having here two commented out lines. If you would like to basically generate the waveform for debugging, then you can do it using these two statements. Okay, dump file, and you give it the VCD file name here, and then you dump all the variables by issuing this system task here. Okay, so we do not want actually the waveform. We just want the comprehensive test bench. We already have our golden output for 100 input pattern. Okay, and we would like to compare our stimuli with the golden output stimuli. Okay, so we first of all open the input patterns for reading, and also open the output, the golden results for reading, and these are the two file descriptors here. Okay, input file and output file. Now, if any one of them is 0, means that the opening operation was unsuccessful. Okay, then I display an error and finish. That's it. All right. If no errors was there, then what do? First of all, I count the mismatching lines by the setting the error counter by 0. So this basically counter here counts the number of mismatch between the golden output and your circuit. Okay. All right. So while not file in the file, this is a system task that checks for in the file. If it is not yet in the file, then run this these statements here. The first one is R. Okay, you're returning here the value returned by fscanf, and in fscanf you are scanning the input file for these three basically information, three comma separated binary numbers. Okay. With an end line or new line character at the end, I0, I1, and S. Notice that when I read these, I0 and I1 and S, they are going to be applied to the unit under test. Okay? They're going to be applied to the unit under test, and then the unit under test will create an output after how much time? After basically by our module here, after 200 picoseconds. Okay, after 200 picoseconds. However, we are just waiting for 10 nanosecond. Yani we are giving the circuit enough time to basically recover the output by applying the input for enough time, and also we are reading the expected Y, the golden output from output file. Okay. After waiting for the output to be to process the input, okay, we can now check if Y does not equal expected y. Okay, now this is very important. I'm not using, notice that there is a difference between this, okay, and this. Okay, so I want exact equality here. Okay, exact equality. It means even if y is a don't care for some reason, okay, and expected y is some value 0 or 1, okay, then the two values will not match. Okay, but if you use just I think if you use this, then the don't care will not be basically covered. Okay, the don't care will actually count as a match. I will have to get back to my notes and also confirm this with you in the next lecture probably. Okay. So basically this line here checks whether y does not equal the expected output. What is y, by the way? Y is the output from the unit under test, which is basically the instance of max 2 to 1. Okay, if y does not equal the expected y, then we just display a message here, mismatch, and then we write what was the input and the expected output. Okay, but we and the output we got. All right, so we write the inputs and the expected y and y. Okay, and then we increment the error counter by 1. Okay, and then this is the end of the while loop. Okay, and then once you exit from the while loop, the file reached the end of file. Okay, we say here if error count is 0, then we print success, all output matched, else we print failure. This is a comprehensive test bench. Just to finish that, we close the descriptors, the file descriptors, the input and output file, and then we issue a finish statement. This is actually a comprehensive test bench. Okay, now I can show you how this works on the shell. So I'm using, by the way, I'm using Icarus Verilog. Okay, Icarus Verilog. This is Verilog. Okay, compiler and simulator. But in your case, you should use something more professional. I cannot use ModelsSim because I'm using Mac here. I need a virtual machine, which I don't have, to run ModelsSim. But basically, in your case, you should use something more productive like ModelsSim or whatever, Verilog simulator or compiler that will streamline your work. Okay. So in my case, I'm using Icarus Verilog. So I need to compile my code. My code consists of basically the module, which is max2to1.v. Okay, let me make sure that I saved all my files. All of them are saved. Max2to1 and Testbench max2to1. I need to compile both of them, and the result will be written to a.out. Okay, a.out, which is an executable file. Actually, I can run it on the shell, and it will basically invoke the Testbench. Okay, Testbench, and it will write either. Okay, it wrote here success, all outputs matched the expected result. Okay, right now. If you want, I can just change one of the outputs and see what happens. So golden output. For example, let us change this output here, or this output here to be a 0. Okay, and this output here to be a 1. So we expect the errors, the number of errors to be 2. Okay, and let us see what happens when we run a.out now. You see, there were 2 mismatches and a failure, and it prints actually where are the mismatches. Here the input is 1100 and 1011, and we are providing a selection line of the selection line with 1. So you should actually output 1011, right? But we are having here what 1011. Oh, okay, okay. Actually, in our case, the golden output is incorrect. Okay, so we are. I just changed it to show you what happens when you get different result. But the actual the expected output is incorrect here, but the golden output is incorrect. But there is a mismatch, so it will be reported by the test bench. Any question here, Shabab?
What changed when you tried before there were no mismatches, but after there were two? What changed?
Yeah, because I changed one of the golden outputs here. I changed these two. This was a 1 and this was a 0. I changed them to a 0 and a 1.
Oh,
So I
okay.
changed actually the ground truth information. I'm saying here, I'm lying here, basically, that this is the correct output, but it shouldn't be actually. Okay.
Oh,
This
okay.
is in my case, I have to, but my Verilog will trust the golden output, and it will say that your circuit is wrong. Your circuit is producing something that is different from the golden output. You see? So in my case here,
Excuse me.
I will, in order to correct that, I will just rerun the generate test files again, so that I get the correct outputs. And if I basically run a.out again, I should get all outputs matched the expected results. Okay? Question?
Yes, about changing the golden output.
Yeah.
Now, based on my knowledge, the golden output is generated by a code. So how the user can change this generated golden output? Because the code that
It
will
was
generate
just, I just changed it for just illustration. But in reality, you shouldn't touch the golden file. I'm just showing you what can happen if you have a mismatch between the two outputs. So the normal scenario is that you have a bug in your code. Like, for example, let us say here, let us say that I'm going to flip SNS complement. Okay. All right. So this is one bug that you can get. Okay. So in this case, I need to recompile my Verilog code. And then you check the output. Of course, the output will be different for every line now. You see, output is actually different in 98 mismatches. Why isn't it 100? Why isn't it 100? Anyone can figure out why isn't it 100?
Because A and B are equal.
Yeah, when A and B are equal, S doesn't matter actually. It would be either A or B. Yeah, it happens that they were equal for 2 times. Okay, for 2 times. So when they are equal, the result will be correct. But when they are not equal, the result will be wrong. So then you come back and fix the bug, okay, and then recompile, and then run again, and then see all the output matched the expected result. Okay, Hassan?
Okay.
Yeah. All right. So this, yeah, go ahead.
So we make the golden output using Python, and then we take the same input and use it on the test bench to verify is it similar or not, right?
Exactly. This is verification. Important. The main function for a comprehensive test bench is to perform verification that your module is doing what is it expected to do. Okay.
Doctor, so why we need the 100 tests? Why not like 50 or?
Yeah, I mean, so basically, what happens is that the more, I mean, when your test is random, okay, the more tests that you get or you do is the better. Okay, but you can. There is also testing again. Probably I've told you this before. Testing is a completely different discipline. Okay, that basically has its own tools and stuff. So we have what we call automatic test pattern generation and algorithms, and there are actually algorithms for generating tests that basically cover high or provide high fault coverage for the circuit. Okay. But for our case, for our purposes, random is okay, and 100 in this case, yani, your input is what is basically how many bits in your input? It's basically 4 plus 4 plus 1, which is 9. So 9 is or produces 512 combinations, right? 512 combinations, input combinations. So I'm just generating 100 combinations of these. Okay, it may not be that representative. So basically, you may want to say, well, I'm going to produce 1,000 because some of the tests are
Similar?
redundant. Yeah, similar. So because you're generating random tests, okay? So you want to make sure that you're generating, but it's not always possible to generate all the test cases, okay? Sometimes it's just take the corner cases, boundary cases, and some random cases, okay? So in this case, for example, if I compile, but I also need to regenerate what we call the Python generate the test file, okay, and then run the test pattern, all output matched, okay, all output matched for the expected test, and I can count the number of lines in the input patterns, and you can see that it is actually 1,000 lines, okay. Okay, so this is what we call the module for the 2-to-1 multiplexer here is basically called what? Called a structural module. We are showing actually the structure of the circuit here. There is also another structure, another module called the data flow model, which is much simpler than that. I'm going to copy this and basically generate a new file. It's by the way, I shouldn't take much time than this, but it should be very simple. Okay, it should be very simple. So underscore, let me call it dataflow df.v. Okay, so let me paste this, and then the only change that I'm going to do is basically remove all of this, because the data flow model actually supports multi-bit operation or bitwise operation. So I have an assign statement, okay, and then y, all right, equals what do I have? S, not S actually, into what?
Easy.
Handed with
I0.
I0, excellent. Or with S, ANDed with
I1.
I1. Okay? But there is a problem here. S is 1 bit. S is 1 bit. So we need to make it match actually the bit width here. Okay, so I will create another signal here, wire. Let's call it, for example, S replicated. And it is basically n-1 all the way to 0. Okay, and I want it to be of size n and all replicating S. So S replicated n times. This is what it means. This structure here is a replication operator of Verilog. Okay, I'm basically replicating S n times, and this is going to be my S underscore replicated. So instead of using S here, I'm going to use S replicated and S replicated. Okay, and you're done. That's it. Data flow model is much simpler than what we call structural models. I'm going to change this to data flow modeling of, and also I'm going to change this to DF rather than just max to 1. Okay.
Excuse me.
Victor,
Yeah. Yes.
can't I just use conditional instead of extending S?
Yeah, you can. Of course, you can use
Yeah,
conditional.
like S question mark and then this or that.
Definitely, you can use this. Yeah,
Okay.
actually, this is even smarter than. So you can actually let me put them both. Okay, y. So you can say it this way: y equal. So you want to test for what? S. Okay. If S is 1, then you output I1. S is 0, you output I0. This is exactly how it is done. Okay, you can do it this way or this way. Okay, both are fine. Okay.
Doctor,
And what about logical ANDing and logical ORing, or logical ANDing?
That's used for if statements. We'll cover that when we discuss behavioral modeling. Okay.
But if we used, for example, S double and I0,
Okay.
not S double and
No,
I0.
this is bitwise. This is bitwise. So bitwise means we are ANDing every bit with the corresponding bit from the other argument. Okay. Now, if you use a double AND, then the result will be either a 0 or a 1. It's not going to be multi-bit. Okay.
Okay.
Yeah. So let us stick with the. Okay. Who suggested, by the way, the conditional?
Me.
I know it's you, but yeah, حسين الشيخ.
حسين
Okay.
الشيخ. حسين
Yeah,
الشيخ.
okay. طيب. So let me stick with your suggestion here. It's better. Okay. So
Doctor,
yeah, I mean, actually, we would like to have code that is much simpler. So now we have our question. Did someone say something?
yes, for the replicated, it will be for S, it will be 4 zeros or 4 ones.
No, it's not 4. It's n zeros or no, not n zero. N s's or n s's basically. Whether s is 0 or 1.
So how will it be like if it's 4 bit? It will be 4 zeros for 1.
Yeah,
4
but
bits for 0.
we are talking about n here. N. If n is 4, you are right. It's 4 zeros. If n is 5, it's 5 zeros or 4. And so on and so forth. Okay.
Okay.
Right. Now we are going to use the same comprehensive test bench to test for our module. We didn't change anything. We just changed the module name. That's it. Okay. So the rest is exactly similar, right? Nothing changed at all. So we can basically go ahead and recompile Verilog, max 221 DF Dataflow, and TB max 221. Let me just make sure that we saved it. Okay. I wish there was an error. There is no error, unfortunately. You guys are, mashallah, lucky. Okay. Just to get you exposed to debugging. This is my intention. Anyway, the output is called a.out. Okay, if you run it, success. It's the same basically. It's exactly the same, but much. Yani compare this implementation or this model to this model. Okay, this is way more complicated than this. Okay. Also, there is what we call finally, this is just to finalize our lecture for tonight. Okay, I'm going to discuss the behavioral data or model of this multiplexer. Okay, so let me add a new file and call it max 2 to 1 behavioral, okay, dot v. So for behavioral, always we use always blocks, okay, always blocks. We don't use assign or structural. We use always. We change the model name to match the file name, and this is behavioral. Okay, behavioral. Okay, I'm going to ask you to write your names for attendance, Shabab. Just wait. Bear with me in a second, okay? And then we will do it in probably 5 minutes. So I have an always block, okay? And this is a combinational circuit, صح? I can say always at any change in the input, okay? And use always at star for combinational circuits, always do that. Okay, do not just list the sensitivity, just buy yourself a peace of mind and use always at star, okay? Begin and end, all right? And then we just want to now basically, you have many ways to basically model a multiplexer. You can have if statement, you can have case statement, you can have also the conditional operator. All of them are possible. However, you need to change or mark your output as a register. It must be a register, okay? Must be a register. Otherwise, you cannot assign it inside the always block. So the assignment inside the always block is called procedural assignment. Procedural assignment, and there are two kinds of assignment. Procedural assignment: the blocking and non-blocking. Okay, the blocking assignment is when you used for combinational circuits, and non-blocking assignments is used for sequential circuits. So here we are modeling a combinational logic circuit, so we use blocking assignment. So why? You can use I'm going to write them all and comment the ones that we're not going to use. Y is equal to S, and then in case S is 1, I output I1. In case S is 0, I output I0. This is the condition, okay? Other one is using an if statement. If S, then Y is I1, else Y is I0. Okay? This is, of course, you cannot use both. It has to be one of them. The case statement, case what? Case S, of course. And then end case, of course. You have an end case. And for the case, you have the case of 0. Y will be I0. And case of 1, Y will be I1, yeah? That's as simple as that. We have enumerated all the cases, so there is no need for the default case here. So again, since this is not, I'm going to use one of them, so I'll just comment out this. One thing that you need to know, even though you have, you can have multiple always blocks, okay? However, a variable or a register can only be assigned or can only be derived using only one always block. If you try to drive a register in multiple always blocks, you will get multiple driver error in Verilog, okay? Which is not allowed and cannot be synthesized, okay? So this is the behavioral model, and it should, by the way, in the Dataflow model, we didn't model the delay, but that's fine, okay? Also here, we didn't model the delay, okay? So just to conclude this lecture, I'm going to change this to be behavioral. And for the behavioral, I need to change my Y to be, I think, wire. Let's leave it as a wire and then compile and see what happens. Okay. So let me go back here and try to compile Verilog. behavioral now. Oh, it worked. Okay. Anyway, so A dot out and all the results matched. Okay. So I'm going to upload all of these files, inshallah, in our team tonight for you. And then yeah, we'll continue. Probably we'll continue using online lectures for the remaining part of Verilog, because you probably will need to review this regularly. Okay, I will also assign you Verilog homework. Okay, and the assignment will be automatically graded. Inshallah, you get instantaneous score. Okay, for your modules. So next time we will discuss sequential circuit modeling and also basically controller and data path modeling, as well as ASM chart modeling. Okay. Let me stop recording. طيب يا شباب لحظة شوي قبل لا تتحضرون الله يعافيكم. Let me stop recording first.